Okay, this is just a quick run through for the Phasors homework, and here we've got Phasor problem 1, and as you can see, for my example anyway, I have a plus 60 degree angle on my voltage and a minus 25 degree angle on my current, and so that means the angle between should be 85 degrees. Let's just check, that looks alright, and then select the phasor diagram that correctly shows the phasors corresponding to these. So we want a 60 degree angle, that looks pretty close to a 60 degree angle, and then a minus 25, that looks much bigger than a minus 25. That's not a 60 degree angle, that's not a positive 60 degree angle. So it looks to me, for my example, that it's number C. So let's see if that works. Yeah, that looks good. And then we can go on to problem 2. And problem 2, we have a resistor and an inductor, and 6 ohm resistor and a 4 Henry inductor. We've got a voltage supply of 8 angle 25 degrees at 3 radians per second. So that means our inductive impedance is J12, J omega, which is 3, times L, which is 4. So J12. And the current, therefore, so my voltage, my Vs, equals 8 times exponential 1j times 25 degrees on 180, because remember MATLAB prefers things in radians. So there's my Vs. So my Vt is going to be just Vs times, now what's that going to be? That's going to be J12, which is my impedance of my inductor, divided by J12 plus the impedance of the resistor, which is 6. So that gives me that. And that's not a phasor, that's in rectangular coordinates, so I need to have the absolute value and the angle, and it's asking for the angle in radians, so I should be good there. So that should be that's 7.155 magnitude and 0.9, let's make it 0.9, and let's see if that works. Oh, I don't have units, so I probably need a voltage there on my magnitude, and they're all good. And then the current, so the current is going to be Vs, so IT is going to be Vs divided by the overall impedance, and the overall impedance is just that number there, right? So the impedance of the inductor plus the impedance of the resistor, because they're in series. There's my IT, and again it wants it in polar form, so we want the absolute value of IT and the angle of IT, and let's see what that is. So that's 0.5963 and minus 0.6708 to 4 significant figures. The units are amps. Let's see if that works. That looks good. So then the time domain expression, well, the time domain expression and the phase shift should be in radians, so that it's going to be that times cosine, and it's 3 times t plus 0.9 volts, and let's see if that works. Yeah, it liked that one. and then the other one is, there's my amplitude, and I'm going to multiply that by cosine 3t minus this time 0.6708 and see if that works. And we're all green. Okay, so problem 3. Problem 3, what are we after? We want the current as a rectangular phasor. So our Vs this time is 10, and it's just 10 because there's no angle. Our omega is 3500. So our Z total is going to be R, which is 8, plus J omega L, which is 3 millihenries, plus 1 on J times omega, which is 3500, times 250 by 10 to the minus 6, 250 microhenries. Okay, so there's our ZT, and we want the current. So our current IS is going to be Vs, which is, as we said, just 10 divided by ZT. So there it is, 0.5279, and minus 0.6174, and I'm wondering whether we need amps for those. Let's try that out. Yeah, we got that right. And then the time domain expression, we need again the absolute value of IS and the angle of IS, and that's 0.8123 times cosine, and now it's 3500 was our frequency, 3500 T minus 0.8634. Okay, and see whether that works. And that looks pretty good. So let's go to the next one, problem 4. Problem 4, what do we got here? We have a current source at 45 degrees, magnitude 2, and we already know the ZC, ZL, and R because we're just given it directly, so that's all right. So then we need to find IC, and so the current. So let's find the voltage first, maybe. That might be the best. So our VC is going to be V equals IZ, so it's IS, so that's 2 times exponential 1J times 45 on 180 times pi. That's our IS, and our Z is going to be 1 on ZC, so 1 on, so ZC, the total Z is 1 on ZC, which is minus 1J, and then plus 1 on our R, which is 4, plus J4 is our impedance there, and let's see what that gives us. There's our VC. Let's just check to see if that works, and we want the absolute value of VC and the angle of VC, and it's 2.263, and this is asking for the angle in degrees. So let's just change that. So that's on pi times 180. So that's VC. So that looks pretty good. Let's just, I didn't actually put those in just now, so let's just submit those answers and see if we got, oh, we got everything right. So let's just, we've only calculated VC, let's calculate IC. So IC is going to be VC, which we've got, divided by ZC, right? And ZC is minus 1j. Oops, minus 1j. Okay, and so that's that. And then we can just change that over. So it should be virtually the same numbers, except this time the angle is 90 degrees different, right? Because we're multiplying by, or dividing by minus 1j. So that's why the angle there, why the magnitude is the same, but in amps, but why the angle is different by, should be 90 degrees. Okay, so that's that. Select a phasor diagram that correctly shows the phasors VS IC. So we want an IC, which is the blue one, at 53 degrees. And that looks like it's this one. Yeah, so all the others, the IC is in the wrong quadrant. Here it's in this top left quadrant, here it's in the bottom left quadrant. That's the correct quadrant, and that's also the wrong quadrant. So IC is only in the right quadrant in number C, and that's how we do it. Okay, problem 5. So now we've got a sum of 4 phasors. So we've got 60 angle 20 minus 100 angle minus 90 plus 40 angle minus 80. So let's just do those. So that is going to be, so 60 times exponential, and what did I say, 20 degrees on 180 times pi, and I need a 1j in there just to make it work properly, and then minus 100 times exponential 1j times minus 90 on 180 times pi, and plus 40 times exponential 1j times minus 80 on 180 times pi. Right, so there's my answer. In fact, let's just put that in that, and then we can say absolute value of total and the angle of total, and so that's 102 times cosine of 150 times t plus, and it should be in radians, 0.908, and let's see if that works. Yeah, that looks good. What is the frequency of the function in hertz? Well, in radians per second it's 150, so I need to divide by 2 pi. That's 23.87. And I don't have units. Let's give it units. And then what is the period of the function? So the frequency is 23.87 cycles per second. So the period is 1 on that seconds per cycle. So it's well, let's just take that number there, 0.0419 seconds, and let's see if that works. And that looks good. Okay, and That's problem 5. I think problem 6 is the last one. And again, we've got phasors, and we just want to add 8. Now, this one's tricky because we've got a sine wave, not a cosine wave, right? So we need to okay, so this is the problem, right? We're out of phase by 90 degrees. So how do we get from sine to cosine? Angle difference between sine and cosine, right? And right, so I don't know whether we've got anything better here. So let's just see if we can do it here. So let's just do that, and that's the wrong way, so we've got to go plus 90, and we're still not overlaying the red one. Ooh, why is that, I wonder? Oh, it's because my cosine needs to be, yeah, let's try that again. Right, there's my sine. Oops. There's my sine wave. There's my cosine wave. And what I really want is something like that. Right, so that actually lines up. So I've got a cosine of minus 90 degrees. Okay, so let's go back to our so I really got this minus 90, so it's going to be IT equals 8 times exponential 1j times, now it's going to be 220 minus 90 on 180 times pi, and then minus 9 times exponential 1j times minus 25 on 180 times pi. Okay, and then I need to get the absolute value of that, and it's radian angle, right? So it's 16.6 times cosine of 5 times t plus 2.5. Let's see if that works. Yep, that looks good. And I don't have another problem, so that is the entirety of